Welcome to the lesson on building metrics. Upon completion of this lesson, learners will be able to describe metrics and their importance in automation decisions, identify and describe the 5 key components of metrics, and analyze robotic automation metrics through a case study. Let us start by defining metrics. Metrics are quantifiable measurements used to evaluate and track specific performance indicators that determine the success and efficiency of robotic systems. These metrics are particularly essential when building a data-driven case for implementing collaborative robots, as they provide concrete evidence and measurable outcomes rather than relying on subjective assessments. By tracking these metrics, organizations can make informed decisions about robotic integration, optimize their operations, and demonstrate clear value from their automation investments. Here's an example without metrics. We want to introduce a machine tending cobot because it will boost productivity. The first question you might ask is, what defines boost? Are we talking about increased productivity or reduced time? These are important questions to consider. Now, here's an example with metrics. We want to introduce a machine tending cobot to a milling CNC machine. This will increase the machine's throughput by 20% over 4 months, improve consistency, and achieve a payback period of 1 year. Notice that in this example, the use of metrics provides factual statements. 20% improvement over 4 months, enhanced consistency, and a 1-year payback period. This leads us to the 5 key metrics used to determine if a robotic automation project will be successful and bring meaningful benefits to manufacturing operations. Number 1 is quality. Number 2 is throughput. Number 3 is return on investment potential, abbreviated as ROI. Number 4 is time, and 5 is value. As we proceed through this lesson, we will look at each of these key metrics in detail. The first metric we'll discuss is quality. Robots are installed not just for speed, but also for consistency, which is one of the main benefits of using robots in the industry today. Robots can perform the same tasks repeatedly with consistent precision, ensuring uniformity in operations. Additionally, robots can eliminate nonconformities. For example, when an operator places a part inside a machine, they might not position it in the same location or orientation every time. However, with the implementation of a robot, the part can be consistently placed in the exact same orientation and spot each time. Here are the 2 questions to be considered. Question 1. How many nonconformities are produced in the cell? This question helps track the quality control metrics by measuring the number of defective or non-standard products produced in a manufacturing cell. For example, if a cell produces 1,000 parts per day with 15 defects, this represents a 1.5% nonconformity rate. This baseline helps identify quality issues and sets targets for improvement through robotic automation. Question 2. What is the total cost of these nonconformities? This question quantifies the financial impact of quality issues. The second metric is throughput, also referred to as output. Collaborative robots have the potential to increase the output of a process. One way this is achieved is by reducing the cycle time, allowing tasks to be completed more quickly, which in turn increases output. Additionally, automating a process with a cobot eliminates the need for an operator to perform repetitive tasks manually. This reduces cycle time inefficiencies associated with human factors such as fatigue or inconsistency, further improving throughput. Some questions to consider are, what was the throughput of the manual process? This question helps establish the baseline production rate before automation. For example, if manual operation produces 50 parts per hour, this becomes the reference point to measure improvement after robotic implementation. And what was the cycle time for the manual process? Cycle time measures how long it takes to complete one full operation cycle manually. For instance, if an operator takes 3 minutes to complete a welding task, this becomes the baseline cycle time. The next metric we will discuss is return on investment potential. Collaborative robots offer greater ROI potential compared to industrial robots due to their lower cost and quicker payback period. Industrial robots are typically 5 to 10 times more expensive than cobots. Additionally, collaborative robots can be more efficient, as a single robot can tend to several machines faster and more consistently than a human operator. 2 questions to consider are as follows. Question 1. What are the costs associated with automating the process? This question examines the total investment required for automation, including initial robot and equipment costs, installation and integration expenses, etc. Question 2. Do the benefits justify the investment? This question evaluates whether the financial returns outweigh the investment costs by analyzing increased production output value, labor cost savings, energy efficiency gains, etc. For example, if a $100,000 robotic system saves $50,000 annually in labor and quality improvements, the payback period would be 2 years, helping determine if the investment is justified. Let's now discuss how collaborative robots impact time metrics in manufacturing operations. Let's look at 3 key ways cobots transform our production time. First, think about human workers. Cobots take over those repetitive tasks, allowing your employees to focus on more complex, value-adding activities. We can also see a significant increase in production output because, unlike humans, cobots can maintain consistent speeds without fatigue. And finally, cobots substantially reduce downtime in your operations through reliable performance and predictable maintenance schedules. Some questions to consider are, how often and for how long does downtime occur? Which are the value-added tasks elsewhere in the process that are currently understaffed? By tracking how often and how long these stoppages occur, whether from equipment failures, shift changes, or maintenance, companies can calculate potential time savings through cobot implementation. For example, if a line stops for 30 minutes 3 times per shift for operator breaks, this data guides automation planning. By mapping high-value activities and current bottlenecks, companies can determine where skilled workers are occupied with routine tasks that cobots could handle. This allows human workers to be reassigned to complex tasks like quality inspection, where their skills provide greater value. The last metric we will discuss is value. Value is defined by what the customer is willing to pay for. By assigning robots to tasks such as packaging or sorting, you can free up employees to focus on jobs that directly contribute to creating value to the customer. 2 questions to consider are, 1. How would cobots affect the value created for the end customer? This question examines how cobot implementation directly impacts customer value through improved product quality, faster delivery times, and competitive pricing. For example, if cobots improve product quality by 15% while reducing production time, customers receive better products faster at optimized costs. And 2, how would cobots impact the value created for the next stage in the process? This question focuses on internal process improvements, where cobots enhance value through smoother handoffs and reduced wait times between operations. For instance, a cobot handling packaging provides perfectly sorted materials to shipping, creating a more efficient workflow for the next stage. Let us look at a hypothetical case study examining the implementation of robotic automation in EV battery assembly, which demonstrates measurable improvements across all 5 key metrics. This table consists of 4 columns: metric, current state with robotic automation, and expected improvement. The rows correspond to each of the metrics discussed in this lesson. In terms of quality and throughput, the implementation of precision robots would increase first-pass yield from 92% to 99% in battery cell placement, while production capacity would improve from 50 to 75 battery packs per shift. The ROI potential shows that the current state has annual labor costs of $250,000. With robotic automation, there's an initial investment of $180,000 for the robot plus annual maintenance costs of $20,000. The 18-month payback period is calculated based on savings. Current labor costs minus new maintenance costs, which equals an annual savings of $230,000. Given the initial investment of $180,000, it would take approximately 18 months to recover the investment through labor cost savings alone. Time metrics indicate potential efficiency gains, with cycle time reducing from 45 to 30 minutes per battery pack and downtime decreasing from 2 hours to just 30 minutes per shift. Value creation for customers would be evident through enhanced quality checks and faster delivery times, improving from 5 days to 3 days, representing a 40% reduction in customer wait time. Let us now look at our lesson summary on building metrics. Metrics are essential for building a data-driven case for cobot implementation in manufacturing operations. When compared to industrial robots, cobots demonstrate superior ROI potential through quicker payback periods, lower implementation costs, and higher operational efficiency. By evaluating 5 key metrics, time, quality, throughput, output, ROI potential, and value, organizations can determine if a robotic automation project will be successful and deliver meaningful benefits to their manufacturing operations. These quantifiable measurements provide a foundation for making informed automation decisions and tracking performance improvements. Thank you.